Assalamualaikum warahmatullahi wabarakatuh. So, my name is Aleiandra Carissa Irawan with ID student F1D02410034. In this video, I wanted to explain about the project, the parallel processing project. Um, so, in this project, I have conducted a performance benchmark comparing the two foundational architecture in Pyspark, the high-level Spark session utilizing the SQL API against the low-level Spark context utilizing the RDD API. For this project, um, it processed a synthetic server log dataset containing 100,000 records. The decision to use synthetic data rather than a real-world dataset. The reason is, first, it grants precise workload control to ensure a reliable timing benchmark. Second, it eliminates unpredictable data cleaning overhead that could warp our execution logs. And the third, it guarantees absolute data structure predictability for distributed mapping. So, moving to the code, this cell is just for installing Pyspark, um, and this is for the standard Python script. So it can generate the server logs.csv with 100,000 rows across four distinct attributes, which is timestamp, IP address, status, HTTP status code, and response time. So, um, mm, this code, the project is a stabilized cluster environment by initializing the Spark session as a modern high-level gateway. From this instance, it explicitly extracts the underlying Spark context, which gives the direct access to low-level distributed resilient dataset. Then, the core of requirement in this project is to aggregate data in parallel to calculate the total number of HTTP, which is 404 errors generated by each unique IP address. So in this project, it with the method 1 implement using Spark session. So the project is load the CSV file into a distributed data frame and register it as a temporary SQL view named log table, and then execute a structured query. This query to accurately benchmark the performance. The entire Spark execution pipeline is tightly wrapped within time library wrappers. And then for the method 2, the project solved the exact same analytical problem using low-level functional RDD primitive via Spark context. This directly reflects the core concept. This reflects the concept of MapReduce paradism from materials. We're using a three-stack functional chain. First, we use a filter lambda to structurally discard non-errors row across the data partition. Second, we apply map lambda to project the data into parallel intermediate key value pairs, mapping each IP address to an atomic count of 1, and then utilize reduce by key to trigger an architecture-wide reduction, shuffling and aggregating the values across matching keys. Just like the previous step, this MapReduce execution is fully timed. And for the result, um, for the evaluation logs, um, actually, which validate the success of this project against the requirements. Um, First, automated assertion returns outputs match true. This mathematical this mathematically verifies that both the high-level SQL abstraction and the manual low-level MapReduce chain achieve identical processing integrity. And second, at the performance benchmark, Spark contacts execute significantly faster at approximately 4.9 seconds compared to Spark section, which took which took 18.1 seconds. So for this performance delta is that at 100,000, the conclusion is at 100,000 record workload, the manual RDD pipeline directly execute linear data transformation without overhead. In contrast, Spark Session activates the full Catalyst optimizer suite to generate abstract syntax trees and structural query execution plans, an administrative overhead that is highly efficient for terabyte scale big data cluster but slows down smaller workloads. Thank you. Assalamualaikum warahmatullahi wabarakatuh.